Welcome to this video on half-life, a key concept for your GCSE Physics revision. We will cover radioactive decay and the practical applications of half-life. In this video, we will explore what radioactive decay is, define half-life using activity and count rates, look at exponential decay patterns, and discuss how these principles apply to the real world. We begin with Chapter 1, focusing on radioactive decay and understanding nuclear instability. Radioactive decay is fundamentally random and spontaneous. It is impossible to predict when a single nucleus will decay. Because of this, we look at the average behavior of a large number of nuclei, making half-life a statistical property. Every radioactive isotope has a unique half-life, determined by its nuclear structure. These range from fractions of a second, which are useful in medicine, to billions of years, like uranium-238, which is used for dating rocks. Next, in Chapter 2, we will precisely define half-life, understand units of activity, and explain what we measure. Half-life is defined as the time taken for the number of undecayed nuclei in a radioactive sample to halve. Note that this refers to the original radioactive nuclei, as others transform during decay. Both activity and nuclei count follow this rule. Activity is measured in the SI unit, the becquerel, where 1 becquerel equals 1 decay per second. Often, we use kilobecquerels or megabecquerels for more active samples. As a sample decays, the pool of unstable nuclei shrinks, causing the activity to fall over time. Activity is directly proportional to the number of remaining nuclei, meaning they share the same half-life. In the lab, we use a Geiger-Müller tube to measure count rate. Remember to subtract background radiation from your readings, and note that count rate, activity, and the number of nuclei all share the same half-life. Chapter 3 tracks how nuclei and activity change over successive half-lives, characterized by exponential decay. Radioactive decay follows an exponential curve, creating a distinct ski-slope shape. In each half-life interval, the remaining amount is halved, meaning the sample never reaches zero but eventually becomes negligible. After one half-life, half of the original undecayed nuclei and half of the original activity remain. Half of the nuclei have now decayed. After 2 half-lives, the sample has halved twice, leaving 1/4 of the original undecayed nuclei in activity. This means 3/4 of the original nuclei have decayed. Finally, after 3 half-lives, 1/8 of the original undecayed nuclei remain. With 1,000 starting nuclei, only 125 would remain after 30 minutes if the half-life is 10 minutes. This slide provides a quick visual reference for the halving pattern. Notice how after each half-life, the remaining quantity of undecayed nuclei is multiplied by exactly 1/2, confirming the exponential nature of the decay. Here is a useful table for your studies. It tracks the number of half-lives, the remaining fraction of nuclei, the percentage remaining, and the fraction that has decayed. Practice completing such tables, as they are common exam topics. Moving to Chapter 4, we will learn how to interpret decay graphs. This skill is essential for extracting half-life values from experimental data in your exams. In GCSE exams, you must be able to read half-life from a graph. The curve shows activity or count rate versus time. Simply choose a starting point, find the time it takes for that value to halve, and read it from the x-axis. Follow this reliable 4-step method. Pick a clear starting point, calculate its half, draw a horizontal line to the curve, and drop a vertical line to the time axis. Repeat the process to verify your result. Crucially, a specific isotope always has a constant half-life. It is unaffected by external factors like temperature or chemical composition. This reliability is fundamental to scientific fields like medicine and radioactive dating. The duration of a half-life dictates how we use an isotope. Longer half-lives result in slower decay, meaning the source stays active for ages. Shorter half-lives cause rapid decay, making them useful but also more intensely active initially. Chapter 5 explores real-world applications of these concepts, specifically looking at how we use radioactive isotopes in medicine and for archaeological dating. In medicine, isotopes are chosen based on their half-life. For diagnosis, like using technetium-99 meters, we need a short half-life to limit the radiation dose. For radiotherapy, we use isotopes to target and destroy diseased cells. Selecting an isotope involves balancing risks. If the half-life is too long, the patient is exposed to unnecessary radiation. If it is too short, it might decay before reaching the patient or during the procedure. Radioactive dating utilizes the constant half-life as a nuclear clock. Carbon-14 is excellent for dating organic materials up to 50,000 years old, while uranium lead dating is used for geological samples dating back billions of years. The core principle is the ratio of radioactive nuclei to stable products. By measuring this ratio, we can work backward to determine how many half-lives have passed since the material was formed or the organism died. Finally, Chapter 6 covers exam techniques. Mastering definitions and avoiding common pitfalls are the final steps to succeeding in your physics examinations. Memorize the definition of half-life, the time taken for activity, or the number of undecayed nuclei to have. Both versions are correct, but be sure to be precise and avoid saying it's the time for a single nucleus to decay. Avoid common exam mistakes. Remember that decay never hits zero. Always account for background radiation in your calculations. Distinguish between activity and count rate, and keep in mind that half-life is constant regardless of sample size. This video shows a worked example for calculating remaining activity. With an initial activity of 1,600 becquerels and a 20-minute half-life, we find the activity after 60 minutes by determining 3 half-lives have passed and having the value 3 times to arrive at 200 becquerels. Next, we find the half-life from data. By counting 3 halvings from 800 to 100 becquerels over 40 minutes, we divide the total time by the number of halvings to calculate a half-life of 13.3 minutes. Always count the number of times you have to find the elapsed half-lives. The fraction method is an alternative approach. By expressing the remaining activity as a fraction of the original, we can determine the number of halvings. This method is particularly useful when the numbers are not straightforward, as long as the fraction is a simple power of 1/2. Review this key vocabulary checklist. You should be able to define terms like undecayed nucleus, activity, count rate, half-life, and exponential decay. Confident use of this terminology is essential for success in an exam context. Use these quick-fire revision questions to test your knowledge. Cover the answers on the right and attempt each question independently first to ensure you are fully prepared. Everything we have discussed connects to the central idea that radioactive decay is random but statistically predictable, resulting in a constant half-life. Keep this core connection in mind during your studies. To summarize, remember the 5 big ideas. Decay is random, half-life is constant for each isotope, the process is exponential, activity is measured in becquerels, and these principles are vital for real-world applications in medicine and dating. The most important exam tip is the definition of half-life, the time for activity or undecayed nuclei to have. Both definitions are correct and equivalent because activity is proportional to the number of unstable nuclei. Memorize this word for word to secure your marks. Use this final checklist to audit your knowledge. If you are uncertain about any of these points, such as calculating fractions or explaining why decay is random, go back and review those specific sections before your exam. Good luck in your exam. Remember to define your terms precisely. Show all your working clearly for potential method marks, and read graphs carefully. You have the tools you need to succeed.